Okay, good morning, everybody, and welcome back to session 2 of this great class. Um, I'm Sue Couch. I'm a member of the Science, Medical, and Technology Committee, and we're really happy to have you here today for our session. Just a reminder to silence your cell phones or any other mobile devices that you might have on you. Also, we want to welcome the crowd that we have joining via Zoom. And a special thanks to Gloria Goodwin over in the back, managing all our technology there for us. And one final thing I want to mention is that there's a special interest group being started on this particular topic. If you want to become more environmentally friendly, you are invited to join other like-minded HASS members for an introductory exploratory session in the HASS classroom next Wednesday, October 4th at 3 p.m. So if you want to pursue this topic going forward and live it, and we're going to learn a lot about it today. This is session 2 of sustainability and circular economy, and I'm so excited that our good community members and partners here from PADNOS are here to talk about the things that they do at their company. Today we have Randy Knibbe is our presenter, and he is Vice President of Sales and Operations at PADNOS. He holds a bachelor's degree in business administration and a double major in operations management and marketing from Grand Valley State University. So he's a local boy here. And a very enthusiastic presenter, as I've had many conversations with him. So let's welcome Randy, and we'll go ahead and kick off our talk.
Thank you. Thank you for that glowing introduction and for our conversations that helped a lot. In fact, Sue and Dave were an inspiration for this second half because we had a lot of phone conversations about how do we use technology and how do we leverage that to increase the recycling that PADNOS does. And so this is the title of the course today, Recycling and the Utilization of Technology. And I thought, wait a minute, that's actually my job description. So hopefully this goes well. I want to thank all of you for being part of this today. I want to thank all of you for this opportunity to be here. Carrie, my colleague, presented last week. Is there maybe a show of hands of who participated in that one? Most of you, excellent. So hopefully some of the introductory slides, we'll just move through them quickly. I don't want to spend too much time and repeat that, but yeah, she's amazing. She's an expert in the field, and boy, she raised that bar high. I've heard a lot about it, so I'm a little nervous, but let's see what we can do here today. I guess before we get started, I'll say a little bit about myself. I am a local boy. Thank you. Even though I'm getting a little gray hair here, I appreciate that. Born and raised in West Michigan, I've been blessed to work for PADNOS my entire adult career. Started 2 weeks out of Grand Valley, been there ever since, 21 years. And I've done dozens of different roles and responsibilities from logistics, quality, non-ferrous, plastics, yard management, recycling centers, and currently I oversee the ferrous side of the business. That's a term that we're going to all learn today. And the experience, the journey has been amazing. Every day we learn something new, and every day the world changes, so we have to keep learning to stay ahead of it. So we'll talk about that. But before we get into that, we'll just do a little background here. PADNOS started in 1905. It's a fourth generation family owned and operated company. We recycle metals, plastics, paper, and electronics. And there are currently 30 locations across the state. So a little history. Louis PADNOS started. It's an interesting story. There's a lot of stories, as you can imagine, in a family-owned company, especially when you get to the fourth generation. Louis was originally from Russia. He immigrated here, but he made a stop in the Netherlands for a year or two, and he picked up Dutch. So when he then ended up in Chicago, he had family there, distant relatives there. They said, hey, there's this Dutch community up in Holland, Michigan. You should go up there. And he did. And he started here, the only Jewish person, I believe, at that time in the entire town. And you can imagine all the things that comes along with starting there, but he started a business and he was peddling and recycling. The term was peddling back then, but recycling rags, newspapers, furs, hides, and of course, got into metals. And I just think that's just such a fascinating story to see that that humble start has gotten to the organization where it is today. And that same culture, that same passion for recycling, of finding value in making, the world a better place, not taking anything out of the earth and not putting anything back into it. It started back then, which is just pretty incredible. So just a couple of dates here. In 1950s, his two sons, Seymour and Stuart, became part of the business. There was growth there. They moved to the location on River Avenue. I'm sure many of you are familiar with that. And then in the 70s, it was a major event that it hit the New York Times, where it was one of the first shredders, automobile crushers, I think they called it. It was this new technology that came out that you could take a vehicle and you could downsize it and crush it and shred it so that it could be recycled. And the Padnes family and Stuart and Seymour at that time had such vision and foresight to see the need for this and put it in. It was the first shredder that was not put next to a steel mill or a major metropolitan area. And so that was why it hit the New York Times. Like, what are they thinking putting that up here in Holland, Michigan? And it's by the water. So 50% of your geography, you can't pull scrap from. What are you going to do? Well, it was a great place to put it. And we'll hear more about that later. And then, of course, today it's the fourth generation, and we continue to leverage technologies and have that mindset and that vision that they created for all these years and centuries and generations. When we talk about recycling, I think Carrie talked about this briefly. In the 20s, we didn't have to worry about it. There wasn't overconsumption. There wasn't waste. Everybody was using everything to its full extent. And then in the 40s, we had the war effort. Everybody became a recycler. And it happened. In the 50s and the 60s, it was kind of when things changed. Plastics was invented. And it was the throwaway. You could just put in these throwaway containers and you could do all this. And this is great and happy-go-lucky for about 15 to 20 years. And it wasn't until the 70s that we realized this is a problem. And Lady Bird Johnson was instrumental in doing a lot of things about this, specifically like the highway beautification projects and things like that, because there's cars being abandoned on the side of the roads. And I think Carrie showed some pictures and things. So it took till the 70s for us to realize we got to get in front of this. When I say us, the general United States. And we had our first Earth Day. Realized right about in the 70s is when the car shredder was put in Holland. So fortuitous timing, right? Here is our mission statement. This is what we at Padnes all live for. So it's our purpose statement. It's what we do every day. We continue to find ways to innovate, lead, and make a positive impact on the world. We may not be able to change the whole world, but we can all, and all of us in the room here and those that are remote, can make some sort of positive impact on the world. The footprint today, here is the state. We've made acquisitions over the years. Last year, 7 locations were added, most of those on the east side of the state. Predominantly, we were the west side. We moved north to Traverse City, down. We actually have one location here just south of the state line in northern Indiana. It's our plastics compounding facility. And then we've been moving towards, so now we have sites and locations where we can collect scrap. And it's kind of like a hub and spoke system where these different facilities provide opportunities for the general population and industry and manufacturing that's in that area to be able to bring scrap to us, or we can collect it, homogenize it, accumulate it so we can efficiently truck it to larger centers like Lansing or Holland or Grand Rapids or Muskegon, where we can do additional processing. Holland is the one that all of you will recognize. Holland, we have actually 3 sites or 3 things going on in Holland. We have our corporate headquarters. It's been there. We have the processing facility. Many of you are familiar with if you're driving down Pine Avenue. And then we also have machine shop, where we have fabricating shop, we have millwrights, electricians, trailer mechanics. The family has always said we want to be like a ship at sea, which means being self-sufficient. And so we have all these services so that if we need to fix our trucks and fix our equipment, our processing equipment, we can do that internally. We're not dependent on someone else. Very interesting thing happened in 1963, and you're not supposed to be able to read this, but this is a new article that was in the Sentinel in April of 63. I don't quite remember that one. And this says, a new firm plans to build a dock on Lake Macatawa. Who would have thought? Why a dock? At that time, it was a swamp. There was no access. What are we going to do with this lake? And this group got together, Seymour and Stewart and a few others. If I can read the names here, maybe you know, Robert Fitzgerald and a Robert Kirchen. But basically, they started the Macatawa Bay Dock and Terminal Company. And they put this plan together that we're going to build a dock and we're going to turn Holland into a port. And they did. It's actually an international port. It's governed by the Department of Homeland Security. We get security audits. There's a protocol. The Coast Guard oversees it. But we are an international port right here in Holland, Michigan. It's amazing. And how they did this and how they built this is like a perfect example of recycling, or what we'll talk about is real cycling. Is when the Army Corps of Engineers was dredging the channel to make sure that the water flow was open out to the big lake, instead of pumping that sediment out like they normally do miles out, and eventually it's going to blow back in with the current and the storms and the winds, they pumped the sediment in. They put in 50-foot sheet pilings and pumped it in behind it and literally filled it up and made usable land. And that's how the dock was created. Just the most amazing story. And it has been utilized ever since. So here's a picture. All of this site right here was created by their ingenuity in this committee that said, we need to put a dock in Holland, Michigan, which is going to help us with commerce. So getting into technology and recycling allows us to take less out of the planet and put less back in. And this was coined by Carlin. He's newer to our team, and he's our chief strategy and marketing officer. And getting that outside perspective of the things that I do every day and Andrea does every day. He's like, it's amazing what we do. We need to explain more of that and educate others so they understand what we take for granted every day. What we're doing is we are truly using technology every day, and more technology than you would imagine. Hopefully I will prove that point by the end of today. And our goal is to leverage technology so we can recycle more materials. I'll just put a plug out there. Things are not being designed for recyclability. They're being designed for what consumers want to pay for. And so that makes it more and more difficult to recycle. So we need to constantly invest to stay ahead of that, to make sure that materials can be recycled. And we do. We heavily invest every single year. I think Carrie touched on this. We call it real cycling. She talked about sustainability. She talked about the circular economy and what recycling truly is versus some of the greenwashing sometimes we hear, versus some of the perceptions or the things that some may think or may feel. Real cycling is what we do, which involves a very extensive process. There's a circle here. I don't know if you can read it. I'll read it out loud. We have to collect these materials, or a plug for all of you, please bring them in, bring them to us. We will recycle them, recommend others who have things, bring them in. We have to separate them. We have to process them. We have to use a lot of science and technology and testing and inspection. And then, of course, it's all the logistics of delivering them out to the consumers that need them, when they need them and where they need them. So this is what recycling and real cycling involves. And I'll just pause here for a minute because we're on a roll. Anybody have any questions so far? By all means, please raise your hand, or online, however you do that, type them in. about anything that we've talked about so far.
Have you used AI at all?
Have we used AI? We are currently using AI more than Chat GPT on the phone, even though that app is very handy. It's unbelievable. We are under an NDA, non-disclosure agreement. This is out there. This is R&D. And what we're doing, we'll talk about it a little bit later on, but we are programming what scrap looks like as it comes across the belt, and we're cataloging it, millions and millions of pieces. And then we're identifying them, we're creating trends, and we'll eventually use that to be able to automatically sort scrap. So right now we're just cataloging things. We're just taking pictures of stuff that we'll use down the road. It's a box, it just plugs in, it just takes millions and millions and millions of pictures. And eventually you tie that to the AI software. Very good question. Any other questions? Anything online? I'll ask you a question then. So real cycling, who here feels they don't have something or some sort of scrap that would be valuable and recyclable if it came to Padness, or if we came and picked it up? Are we able to convince and educate everybody that everybody can be a recycler? Okay, good. Carrie did a great job then last week. We're going to get into the metals. On the metal side, we have, we basically decided, it's split into two different types, two buckets. You have ferrous. Someone want to guess what the other one is? Non-ferrous, very technical, right? One is and one isn't. Ferrous is actually comes from Fe. Fe is iron. So everybody remembers their chemistry classes. Boy, some days though I wish I paid more attention and weren't fooling around with the Bunsen burner, see how high I could get. I know my lab partner, she wasn't always impressed with me, but we had a lot of fun. So iron is ferrous, and a car would be an example of mostly ferrous metal. There's also glass, there's plastic, there's some non-ferrous metals in there. Iron is the fourth most prevalent element in the earth. Anybody want to guess what number 1, 2, and 3 are? Put you on the spot. Aluminum. Now, normally, if I'm doing this like at a school, I'd give you a prize or a sucker or something. I don't have anything. Thank you. Aluminum is number 3. Number 3 comes from bauxite. Very high requirement of energy to make aluminum. So an interesting fact, aluminum is the most recycled metal out there. About 98% of all aluminum ever made, late 1800s, I think they figured out how to do it. It's still being used because it's so much cheaper to just take refined aluminum and just melt it down and use it again versus, getting the bauxite and mining it out of the ground. Number 2, think of the state park out here. Think of the sand dunes. Silica, which is silicon. Think of the Sahara Desert. Think of sandstone and the ground underneath us. And number 1, a little bit tricky, but not really. We're breathing it every day. Oxygen. Oxygen. So those are the 3. Iron is Fe. Quick tip. Steel is mostly iron. You put a fraction of a percent of another element, manganese, maybe a little chrome, maybe a little nickel, some carbon, and it's 1,000 times stronger. So that is and that's a high version level of steel, but iron is Fe. Iron ore mined out of the ground is 65% Fe. Steel is like 99 point whatever, or 98. So it's a refining process with a few other elements put in for an alloy. Non-ferrous side. Oh, I missed one thing. On the ferrous side, and I'll go back here, it doesn't like me. Okay. Fe is magnetic. There's 2 other elements that are magnetic, nickel and cobalt. That's it. Everything else is non-magnetic. So every good scrapper or recycler or someone bringing scrap in should have a magnet. I carry mine with me all the time. And if it sticks to a magnet, it's ferrous. If it doesn't stick to it, it's non-ferrous. Very simple, but we use magnets all the time. So a couple examples of non-ferrous metals: copper. A can, if that's a tin can, that would be tin. If it's an aluminum can, it'd be aluminum. Nickel. Nickel's too valuable today to make a pure coin out of nickel. Might be a little bit in there, but like 1% or something like that. It's an alloy today. But that's where the term nickel came from. There's stainless steel, which is actually not a base element metal. It's a alloy of chrome and nickel and a few other things. But you have aluminum, copper, nickel, tin, lead, and zinc are the main non-ferrous metals. So now I want to switch back to a car, because we talked a lot about cars. Cars are a big source of supply of scrap that need to be recycled. In a car, when you dissect a car, when you break it down, 65% ferrous or steel by weight, 30% non-metallics, mostly non-recyclable, and then only 5% non-ferrous. It's all together in a car, and it needs to be separated to be able to be recycled and to be recovered. So that's where the technology comes in place. So I'm going to walk through this. Hopefully you can see it. We get your scrap, think a car, we shred it. That allows you to separate it. From there, and we'll get into this, we use magnetic separation. So we pull, now, the ferrous from the non-ferrous, and the non-metallics obviously aren't magnetic either, so that would drop out. Then we blow some wind on it, use some cyclone action to clean it up. We do ballistic separation. We'll get into that. At the end, we still do some manual sorting to see if there's anything that our technology missed. And then we make a variety of grades of number 1 shred. I'll hold this up right here. This is what a shredded car looks like. Pieces of popcorn, typically the size of your fist, and a lot of them. All ferrous, sticks to a magnet. Think of what's in the car: the seat belt, the foam, the fabric, the plastic, the glass, the headliner, the shoddy, the insulation, all the electrical wires and circuit boards that are in there, all taken out. Basically, upper 90% Fe content right there. It's going right back to a steel mill. They're going to make coil. It's going to come right back to a assembly plant, as long as they all don't keep striking, and they'll make another car, and it just closed loop. Cars nowadays have about 90% recycled content in a car. It just closed loops it. So let's get into the technology. This is what the downstream of a shredder looks like. We have the privilege, it's been a multi-year project to put a new shredder in. We did the one in the 70s, another one in the 90s, and then this one. So it's like every 30 or 40 years, Patnus invests into this. Major investment. This is a 50 to hopefully 100-year project. Once you put one of these in, it's the upfront cost. It's also the investment to feed it. It's a hungry machine. This machine right here will eat, recycle 1,500 cars a day, or the equivalent of that by weight. We don't always just shred cars, washers and dryers, refrigerators, once all the Freon and everything's been recovered, your filing cabinets, your bicycles, your old grill, a chair that has anything that has metal, ferrous content primarily, can go through this operation, and it's intense. This is a 40-acre site. We have 6 acres of concrete that's about 12 inches thick to hold the weight. And then you'll see all these different technologies that we leverage to take. Let's just use this car example and how we separate. So the first thing we do is magnetic separation. I'm going to do some pointing here. I don't know if it works on there. Once you shred it, this is what a shredded car would look like. All of those combinations of materials are in here. It's introduced to 2 drum magnets. Here's a close-up of it. And years ago, that was a rare earth magnet, a solid magnet, which is made out of, it's an alloy of niobium and other elements. Now they're electromagnets. Everybody knows what an electromagnet is. You take a coil of wire, wrap it around really, really tight, around a nail, like in science class way back when, put electricity to it, and now you've created a magnetic current and a magnetic pole, or draw, as we call it. These both have electromagnetic elements in it. The shell of the drum is stainless steel, which is non-magnetic, so that the metal pieces won't stick to it. So these pieces come up to that drum and the magnet sucks it to this outer shell, which is non-magnetic, and it carries it over to the next position. Underneath this magnet is a hole in the conveyor, and anything that didn't stick to that magnet drops down below it and goes a different way. So it's a very simple process. It's a very clean cut from non-ferrous and ferrous, and it's done with magnet. I think everybody understands that technology. From there, we use wind and we use air to separate. So typically what happens, you have the cyclone action, just like a tornado, and you can suck anything that might still be mixed in with that steel, with that ferrous shred, a little bit of some foam or a little papers or fuzzies, or maybe a little dirt that was in the carpet from shoes or underneath the car that's just been carrying there from driving a car on a gravel road for 30 years or something like that. And so we take the wind and we blow the wind on it. We can drop the material through the stream and blow up to levitate that out, get sucked out, dropped out on the bottom and collected. And now we've cleaned that steel. This is the latest technology. There's very few of these in the country. It's called ballistic separation. And this is one here we just installed. Basically, here's what we're trying to do. See that? Anybody want to guess what that might be? It's copper wire. And copper is non-ferrous, and copper can't be with the ferrous. The steel mills don't like it. We got to pull it out. However, it's mixed with steel, which is magnetic. So there's a very technical term for these. It's a real term. It's a commodity description. It's called meatballs. Anywhere in the world, you say you have meatballs, if it's in the recycling industry, they'll know these are electric motors that are coming out of the shred process. Think about your alternator. Think about your starter. Think about your water pump. Think about your air conditioning pump. Any electric motor, power windows, right? They all have electric motors. The electric motor is a rotor and a stator and copper wound around it. And that's how electric motors are made. So when we go think about the magnet, those drum magnets were strong enough to pull this over. There was enough ferrous magnetic draw to pull this over. So now we have contamination. That's not a good thing in our scrap. So what we do is we use this ballistic separator. So the material's fed in on your right-hand side. This conveyor goes thousands of feet per second, and it speeds those things up and it shoots them off the end of the conveyor. At the end of this conveyor, there's a magnet. Again, another electromagnet that we can control exactly the frequency. And you know, inertia and momentum, those physics terms, going back a ways there for some of us, for me especially. We can determine at a certain speed. Think about that meatball. Let's just say it weighs 10 pounds. 2 pounds is copper, 8 pounds is steel. You have a 10-pound unit, but only 8 pounds of it are magnetic. So we tune it just perfectly with the speed and the power, the strength of the magnetic pull, that anything that isn't all steel won't be able to stick to that magnet, and it projects off because it has a momentum, and the magnet is set to not quite catch that. Anything that's all steel, 10 pounds out of 10 pounds have magnetic pull. Those meatballs only have 7 or 8 out of 10 pounds, and it separates them. So we're using ballistics and we're using magnetics and replacing what for years was a whole bunch of people sorting by hand. That's pretty amazing technology. It has to be finely tuned. It's not easy to run in, but it's very cool. Okay, that's the ferrous side. Now we have 65% of a car in a form like this jar up here that's ready to go directly to a consumer, like a steel mill or a foundry. They'll pour it right into their melt. They'll melt it. They'll make new coil. They'll make more I-beam, whatever they have, re-rod, construction components, and it's right back into use again. Any questions on that? Because this is the easy part, by the way. This is the least technical part.
What's the
On the
target?
shred,
Yeah.
the target level on the shred for ferrous level is 92 to 96% Fe once they melt it. There's still going to be some slight attachments, different things, and the mills will melt it, and they'll do what they call is a dead melt. They'll melt it all by itself. They know the weight in, they know what they pour out, a little bit of slag on the top of some impurities, but it's a high recovery. Absolutely. Any other questions? What about tires? Good question. So we disassemble a lot of our cars. We don't have an assembly line. We have disassembly lines. We like to take the tires off. They have no value in the shred stream. They're rubber. And tires have steel belting. So what's going to happen when the tires get to the magnets? The magnets is going to think it's steel and they're going to pull them over. And they're going to get into a stream. Then we're going to have people to pull them out by hand. That's the only real way to do it. So we take them off before. Another reason, two reasons. One, we recycle the tires. There's some different opportunities for recycling cars. Number two, a lot of the wheels nowadays are aluminum. And it's better if you can take that aluminum wheel off with the tire, de-rim it, just like the tire shop, take the rubber off, that goes to a recycler, take the aluminum rim, and that goes to an aluminum smelter. And it's more value that way than if it's all shredded together in the car. Good question. Another question in the back.
You may get to this later, but 2/3 about of a car right now is ferrous. Can you project like 10 years for electronic vehicles?
Well, okay, you got me there. There's less and less steel being used in a car every day up until electric vehicles started raising its head. So with vehicles, we want lightweighting. We're using thinner gauge, higher strength, think alloys that are stronger. Technology has allowed us to make things thinner, but still strong. There's way more aluminum being used in cars, also part of lightweighting, and a lot more plastic, and even getting into some carbon fibers and composites and things like that. So I would normally say there's going to be less and less steel. There's going to be more and more non-ferrous. Cars today with electronics, remember the chip shortage after COVID and how many computer chips and how much wire is in a car versus 20 years ago? It's growing exponentially. Electric vehicles changes the story. The batteries are so heavy that they actually are beefing up the cars. The cars are way heavier. If you drive an electric vehicle, Dave, I think you drive one, right? A Tesla. It's heavy. It weighs more than my big Suburban that my wife and I and our 5 kids drive around, right? It weighs more than a full-size pickup truck. They're so heavy and the battery is heavy. So you need to beef up the supports, the springs, the brakes, everything. And weight isn't as much of an issue because they're so efficient. They're so powerful. Electric motors have so much torque. It doesn't matter. You just got to carry that battery. What matters is the battery and the weight. There's the energy, like the horsepower in an electric vehicle, just phenomenal. So now we're seeing this trend with more electric vehicles. We're going to actually need more steel and more high strength materials in a vehicle. So we'll see what happens if the lightweighting of gas vehicles wins or if the electric vehicles wins, and we'll find out. Depends on the amount of battery, like what happens with battery technology, because that needs to improve. The biggest thing that'll slow down the accommodating in the growth of electric vehicles is we don't have the infrastructure and we don't have the power generation to keep up. Like, hey, we're going to be 2035, we're going to be this percent electric vehicles. We don't have the grid to support it. We don't have enough electricity right now to support it. So those things are going to have to, I don't know which one will be the bottleneck first, but there are some bottlenecks to the growth. Amazing technology. Great question. Another question?
So you describe the process of getting the car to the point where you could shred it.
Yeah.
And so we drive by on Pine Avenue. Are people taking tires off cars in that facility, or does that happen someplace else?
Good question. So not in that facility. So that is an industrial site. These cars have already been processed and prepped and drained. We take the battery out, the catalytic converter out, the tires, the rims, the fluids are all drained. the air conditioning system, all of that has already been taken care of. And typically those are done at all those other sites. Like Black River, Carrie talked about that. You would do something there, then you crush the cars so you can maximize weight and space and have fewer trips. So you can be efficient in your logistics. And then that would come to here on Pine. And once it's there, we want it prepped and ready to go. It's an industrial site. We have a question in the back.
Will processing electric vehicles require more labor to remove batteries before shredding the rest of the car?
Absolutely. Until we figure out a quick way to do it, batteries are great until they're not, meaning it's a thermal runaway event. And if you've ever seen a battery fire, Google it. It is amazing. So like amazing in a bad way. It's very intense. It's a very violent reaction. So engineers, and don't worry, you're safe. Very few of them happen. Like the statistics are, it's very, very rare. Yeah, when you look at the statistics for the number of vehicles out there, but when there is one, everybody hears about it. Those batteries are tucked in and engineered to be so protected that they're not easily accessible to get out. And that's part of the design for recyclability. You got to look at ways where you can get them out easy and you can just slide a new one in and slide an old one out like an electric high-low or something. We're not there yet, mostly due to the safety consideration. The other thing with batteries is before you remove them, you need to be highly skilled and highly trained. There's so much electricity there that you got to be able to disable the battery, got to know what to do. You got to be careful with what tools you're going to have. You do not want a spark or an arc. You're dealing with high voltage and a lot of energy packed in one small area. So we're seeing some, but not many, and we're working towards getting prepared for that. An idea for another course would be electric vehicle recycling and all the work we're doing on that, or electronic recycling, because those are new areas where there's a lot of technology and R&D, quite frankly. We don't quite have all those things figured out yet. Any other questions from the remote? Okay. So on the non-ferrous side, I'll just point to this again if that works. We already talked about the shredding side and the magnetic separation. Everything that dropped below those magnets is either the non-ferrous or the non-metallic. In our terms, we call that fluff. So the first thing we want to do is we want to debulk that. And then we want to take just the fluff side out. That goes to the landfill. That is part of recycling vehicles. There's nothing else that can be done with that today. And actually the landfill likes it. They use it for a topper material, right? It's a cap. So it's very beneficial to them as part of the landfill process. But we want to debulk and make sure only things that are in the landfill go there and all the rest of the items can be recovered. At this point, it's ASR, automotive shredder residue. And if you're in our industry, it's the buzzword that everybody's talking about. Because this is a mixed stream, and this is green because it's money green. This is where all the non-ferrous metals are. This is even where some precious metals can be found. And this is where a lot of technology and work is to try to recover this. This is the hard part, but it's a lot of value, and we need to figure out how to recycle it so we don't have it go here. So Patnus is very committed to that. It's green in many ways. It's green for the environment, it's green financially, and it also pushes us to continue to invest in research and development to figure it out, which we always like to do. We like to challenge ourselves. We go through eddy current, we go through air separation, and we pull out all these different metals. We use induction sorting, and then there's still a little portion here that's a byproduct at the end. So debulking. What we're doing here is we're sizing the material into two different sizes, about an inch, inch and a half and down, and an inch and a half up to about 4 or 5 inches. Then those streams are introduced to airflow, blowing up the velocity of the air, the direction of the air, and then also the suction on top. And we can carefully clean and pull out the fluff, the fuzz, the non-metallic side. But we watch this every day. We don't want to blow too hard to take out the valuable material because we want to recycle that. So this is something that allows us to do some separation and processing right on site of the shredders on the non-ferrous side. Then from there, it goes to our downstream plant. This is what it looks like. If you looked at it, You would literally think, hey, that's just a pile of junk, or I don't know what you would call it. You get close and you're like, oh, look at that. Nice piece of cast aluminum. Look down here. Well, stainless. What is that? That's another piece of aluminum. This is rich. This is 28% non-ferrous by weight in this stream. It does not look like it, and it's very convoluted, and it's all mixed together, and we got to figure out what to do with this. Before I show you that, up until this technology came in place, almost all of this was loaded in containers decades ago, went overseas, primarily China. They'd have a mountain of it. There's pictures of this. Go online, you can see it. Thousands of people would line up, grab a bucket, carry it over to their spot, have 5 or 6 bowls, one for copper, one for aluminum, one for this, and literally squatting all day long, bending over, would sort this out, bring their little bowls in of all the metal, get their $1 or 50 cents, and then do that. And just armies of people did that. Another reason why we're going to leverage technology. This is valuable material. We need it here. It's the raw material we need in the United States. So we're going to leverage this technology. First thing we have, these yellow units down there, those are eddy currents. Anybody a kayaker? Know what an eddy is? Yeah. When you see that, you get some stones or whatever, and the current goes like this. An eddy current is what they call, I'll try to explain it. You know how you have your magnet and you have a North Pole and a South Pole, and when you put 2 magnets together, they'll repel each other. There's a drum in the, think of a drum on its side horizontally. There's 2 of them. They're electromagnets. One's running forward, thousands of RPMs. The other one's running counterclockwise. So I should say clockwise and counterclockwise. And they both have a magnetic pull, north and south, but when they're running opposite directions, that pull is opposite of each other. So basically you're taking this magnet and you're flipping the poles thousands of times. And for whatever reason, because I'm not that smart, right, Andrea? Yeah, for whatever reason, it takes non-ferrous metals that are not magnetic. You know how you push a magnet together and it jumps away? It literally repels. It throws that metal. If you watch this in real time over these eddy current machines, aluminum just is sailing off. It's just shooting it off it. And the further it shoots, the cleaner the metal is and the different kind it is. So we put divider plates in there and we can separate primarily aluminum and a little copper with these eddy currents. And again, we have actually 4 rows of these because different weights and sizes of material have different trajectories, different mass. So we have to have different settings. So we size it all into 1/2 inch and 1 inch and 2 inch and 4 inch, but it's the same technology being used. And then here's an example in the plant. We have just a short video, but you can see the small and then medium. And if you kept looking, they're different sizes. This material then gets conveyed through the plant to the next tech. Or just a quick video there. So then we use wind. This technology is called wind sifting. And people laugh when I use this example. I still remember as a kid seeing a picture or reading in a book in the medieval times where they're taking like a person's taking like a rake and they're winnowing wheat and they throw it up in the air and the chaff blows away on a windy day and the good wheat falls down, and it's called sifting wheat, I believe. That's what we're doing here. Except for we're producing the wind. The material falls down through a chute, and we're setting the amount of wind up to levitate out the things that we don't want, typically the non-metallics, just to get that. Any dirt, the glass is heavy, that falls down. We got to get that further along. Any seat belts, any fabric, any foam, any things like that. All those type of things are pulled out with a wind sifter. Technical terms that we use. It's amazing to see. It works very well. All computer controlled, of course. All right. Then we use induction. And the best way I can describe induction is we have a metal detector. Just like you have at the beach, looking for coins, looking for metal. It's the exact same technology, except for we have 86 of these things underneath this conveyor belt. And when it detects a piece of metal with a lot of math and timing, we know that metal detector number 72, which is right here, is going to come right down here in 2.6 seconds. And as soon as it gets to the end, there's a jet of air. It's exactly what it sounds like, shooting these little pieces of metal out. It's like target practice. You got to time it in. And just to give you an idea, we're processing up to 2 million pounds per day. These pieces are well less than a pound. So we have tens of millions of pieces that we're recovering compared to sorting all those out by hand. So this is pretty amazing technology. Now, when you get to the bigger stream, the air isn't strong enough to eject it. Padnis built this. It's like a piano, like a keyboard. We have what I call fingers. And what they do is they're like a pinball machine. So once the metal detector detects the metal piece, when it comes over here, you time it just right, and number 4 knows it needs to fire, and it literally flicks that piece of metal and out of the stream, and that's how it sorts it. We built this in-house with our own engineers. I haven't seen anything like this in the industry. Very cool stuff. We all signed NDAs before this class, right? I'm just kidding. There is an example. So the pieces that it's missing are non-metallic. A piece of rubber, a little piece of glass, fabric, foam. And you hear the clanging noise, which is cool. Whoops, yeah, go back. That is every time you hit a clang, you got a base hit. You got it out. Pretty incredible. Doesn't always work perfect. We got to watch it. We have a high-speed camera. We slow it down, and we see in slow motion. Oh, we fired a little early, fired a little late. We constantly have to be checking and monitoring that. With the volumes we're putting through the facility, if you're missing, if this one isn't firing by the end of the day, you're losing a lot of material that could be recycled. So, okay. You ready for the next one? XRT, X-ray translucence. This is using X-ray in a very controlled manner. And it's shooting the piece of material with an X-ray, giving it energy, and a detector underneath the belt measures the energy. Basically, the piece is vibrating a little bit. So let's go back to chemistry class. You have the periodic table of elements, and you have the lighter elements up top and the heavier ones based on the atomic mass. That's what the numbers are for. Look at aluminum, it's 13. Look at copper, it's 29. It's twice as heavy. If you use the same amount of energy with an X-ray on aluminum or on copper, the aluminum is going to vibrate roughly twice as much. And the machine is going to know, wow, that piece is moving. This one isn't. You program it. That's aluminum. This is copper. We can sort it. Isn't that amazing? That's wild. It's this magical yellow box. Incredible. Now, I'll give you another example. What do you do when you have aluminum, which is 13, and you have magnesium, which is 12? We're at the, at the atom level. Like we're talking very hard. Machine can't segregate that. No problem. Machine can do this. Machine has a 3D laser. It can take very quickly, like so fast. There's so many materials coming across this belt. It's being introduced to this machine at 600 feet per minute. And it's actually can read the size and the shape. So if you always have something round like that, that's an airbag canister. Got to pull those out. Those are from your airbags. Can't have that go to the customer. If they melt that, it could cause a mini explosion. Those got to get pulled out. Well, we know it's a cylinder. It's about this big and it's round. Laser will get it. Not always. That's where you leverage AI. And if the shape doesn't help you, because a lot of shapes are maybe similar, you still have camera. You can do photo recognition. Just like my smartphone here, I can look up my wife's face and it'll find in all of my 50,000 pictures, it'll find everyone. Same technology here. And you can do color recognition. Color is great for circuit boards because circuit boards are green. Have a couple right here. Everybody knows what they look like. Green looks a whole lot different than a lot of these other metals, right? It'll stick out. Used to hire people to just stand there and pull out circuit boards. Now we can do it with a computer and with this machine. Circuit boards. What's the value in a circuit board? gold, silver, palladium, platinum, copper, precious metals. You recover them, can go right back into the circuit board. All these little pins here, they're all gold, 18 karat gold. Not very much of it. It's a thin layer, but it's in there. Okay. So then we have copper wire. So copper wire that's in the car. Now, this is an example of copper wire that you could bring in if you're doing a do-it-yourself at home project or you're an electrician or something like that. This needs to be recycled further. And we have copper wire, just some examples. It comes in different thicknesses, almost always has insulation on it because it's conducting electricity. So they need to cover that. And that insulation we need to get off so we can recycle the copper. So what we do is we run it through a copper chopping plant. Again, there's a shredder. You see it right there behind it, shreds it up. Then we put it through a granulator, which gets it down to a smaller piece. And by cutting it small, you've liberated the insulation from the copper. Then you run it through, this is called a density table. And what we have is a screen, a perforated screen, and it's vibrating, and it's shaking all these pieces. And the dense copper staying at the bottom because it's hard to lift that as much as the insulation. The insulation's bumping up about an inch. And then you have a fan underneath and a suction on the top. And all those pieces that are bouncing higher than the copper, they just get sucked right off the top. And you get out the end, you can do a little bit of sizing. And when you're done, see it moving there. It's vibrating to agitate it. And we're using wind and air to separate it. When you're done, 99.99, sometimes we can go to 4 decimal points, pure copper, right back into electrical wire, copper tubing, maybe even to an application of electronics or anything else that copper's in. Copper's in brass. So think about your faucets, anything brass that you have in your house. 100% recycled, melt right down. It's 99.99% pure. So you're going to have a really, really high yield here. Versus a copper mine down in Chile, bringing that all the way up here into the United States. How do I know that it's 99.9%? We do a lot of sampling. We do a lot of testing out in the yards. This right here, this is a handheld analyzer. We call it a gun. And I was talking about it once at a restaurant and people are giving me a funny look. So now I call it an analyzer. I'm like, hey, is your analyzer working? That sounds a whole lot better than the other one, but it's a handheld device. $20,000 to $30,000 a piece. We have dozens of them. It's necessary for our business. And it can instantly tell you what is in the scrap to identify scrap, especially the alloys. As we make more alloys, it's harder and harder to recycle it. We need to know what it is so we can know how best to recycle it. So we'll do testing there. It's basically a handheld spectrometer using X-ray fluorescence. That's a whole nother course that someone else is going to have to teach. We will melt these copper chop samples in a little laboratory furnace. We'll make what you call as an ingot. There's all retains from every batch that we run. All these ingots now go into the spectrometer. I think I have another, here's our laboratory spectrometer. That's incredibly accurate. And that's how we can guarantee the quality of our copper so it can go right back into the highest and best purpose for reuse. A lot of science there. Just briefly, this is a third-party app that we made that ties into our our ERP system. It's on a phone, dedicated inspectors. Every single load that comes into Padness and every single load that leaves needs to have an inspection, needs to have 2 pictures, needs to have everything documented, got to control the quality. We need to understand what it is so we can get the best use and best repurpose out of those materials. Again, an example of leveraging technology. We have a drone, we take pictures, we fly over a yard. We're even looking at some technology to figure out how to do inventory, where you can fly over your facility. It can triangulate how much volume, you plug in the density and it says, hey, you have this many tons of this and this many tons of that, this many pounds of the other thing. So just technology being used here with inspection, with apps, smartphones, tablets, drones, things like that. And that's just what we do when we shred a car or a bicycle. Just one stream, a big stream, an important stream, a growing stream of material that needs to be recycled. And there's a need for it on the commercial side to consume that. Otherwise, we're going to be mining new materials out of the earth, which we don't want to do. So that's that. There's some additional processing we do. This is our hot briquetting plant. There's only one in all the United States. It's right here in Holland, Michigan. There's two in all of North America. We basically take turnings, is what we call it. Top corner there. That's from, if you ever drilling a piece of steel, this is the little curly Q that comes out. Machine shops, tool and die shops, CNC machines. This is very, it's not very dense. And you got all these balls and all these little like slinkies running around. What we do is we homogenize it. We crush it through a mini shredder. We put it through 1400 degrees in our briquetter, heat it up, and then we have a press with some dies, and it molds it into a briquette. This is hot briquetted steel. It looks very similar to HBI, hot briquetted iron. It's a direct replacement for that. So instead of going up to the iron ore mines, northern Minnesota, that are 63% Fe content, this is going to be 85 to 90. Made with a material that's out of a material that's very hard to recycle. Doesn't transfer well, it's hard to handle. Right here, nice, dense, dump it right in your furnace. Only one in the country that has one and does one of these. Pretty amazing. Baling is compressing. You have to compress loose, voluminous materials that we can then be introduced into a furnace, both on ferrous and non-ferrous. It's hydraulics, it squeezes it up to a certain shape. I don't have a picture here, but if you think of a beverage container, pop can, aluminum can, it's very light, 14 grams is what they weigh, between 14 and 15. That bale right there will weigh 2,000 pounds. So someone get your calculator out, tell me how many pop cans are in one bale. 66,532-ish. So that's the technology we use. We talked about shredding. We have a shredder in Holland. We have a shredder in Grand Rapids. We have a clip shredder in Lansing. We have the new shredder I just talked about that we're installing in Howell. And then we have a handful of smaller, the turning shredder, and then the copper wire shredders, 2 or 3 of those. So shredding is a big part of our business. Basically, a rotor with what we would call hammers. They spin around, they cut the material off, beat it all up, knock it all together. There's a lot of collisions. They call it full box shredding, where all these pieces are hitting each other and they wad up. So it densifies, but it also liberates. That's why we shred, is we have to liberate the non-metallics and the things that aren't recyclable from the stuff that is recyclable. And then, of course, all of this stuff has to be transported from point A to point B. We have 100 drivers, over 100 trucks, 650 van trailers, fleet of 75 rail cars that are ours. If you'll see them coming into Holland here, they say PDNX, Padnos, not CSX. So that's pretty cool. We like that. But we have to move this material. There's a lot of a variety of different types of equipment that all are used to collect the scrap and to deliver the finished product. Rail car. The one I like the most is the barge story. So we talked about the Holland dock. If anybody wanted to know, the official location code for the Holland International Port is USHLM. Maximum vessel was 211 meters with a weight of 30,000 tons. And we actually did one in the 70s, an international cargo. Haven't done it since. My goal is to do one before I retire. Hopefully I got a lot of time before that happens. But we loaded it here. And again, we had to go up to Muskegon to add more weight because the draft in Lake Macatawa is only about 21 feet. So we put about 12,000 tons on this, went up to Muskegon, got it up to 17,000 tons, then went all the way up to the St. Lawrence Seaway. They topped it off with another 15,000 tons, and a 30,000 ton vessel went across the Atlantic Ocean and to some steel mill, and I think it was Turkey at the time. So amazing technology. We're doing exports right here, offsetting our trade deficit in 1970s. I want to do it again. What we typically do is what we call a Laker barge. This is 5,000 tons on one barge. Yeah. So if you figure about 30 tons on a truck, this is 150 trucks that don't have to go down the road. And Dave is going to do some math for me here, right, Dave? We talked about this. We have 150 trucks. And if you're trucking, you're going to go more regional. You're going to go to Gary, you're going to go to Detroit, you're going to go to Cleveland. So figure 300 miles. If you're lucky, a big semi, a big rig might get 4 to 5 miles per gallon of diesel fuel. So Dave and I talked about this, but it's about 100 gallons per trip. That's just easy math that you're doing with 150 trucks. So you have 15,000 gallons of diesel fuel for this one barge. This one barge might take 1,000, maybe 2. He didn't really give me his exact fuel mileage, and it's per nautical mile, not per land mile. But anyways, the point here is the emissions, the efficiency, the one bill of lading, all those trucks not on the road, all those drivers, the requirements that it's just such an efficient and environmentally friendly way to ship product. And it also is much cheaper. And if you think of the Great Lakes, I have a few other facts in here if I can pull this up. Yeah, I mean, we'll do 30 cargoes. We'll do 150,000 tons by barge in a year. And if you look the facts here, last year, 76.4 million tons were shipped by U.S. flag vessels on the Great Lakes. Think of how many fewer trucks. I can't even do that math. It's just incredible. It's such an efficient and good way of shipping. And then once you're off the Great Lakes, what you can do is you can get into the river system, and now you can get down into the interior of the United States. So first of all, there's not even that much of trucking capacity to even move that amount of tons. It's cheaper. It's so much, the emissions and the carbon footprint are just exponentially lower. That is the value of the Holland dock, of having an international port here, not only for us, but for brewers and for Plank. And when we had a coal power plant here, that it was critical. If you wouldn't have a coal plant here if you don't have a port. Getting technical here, but there's a lot of technology. Anybody been on the Badger or know where that is up in Ludington? The same company that owns the Badger owns this barge. This was a ferry, a car ferry. Cut it right off, put some sides on it. They cut the back out so that the tug could go in. It's the only tug on the Great Lakes that has what they call a notch. Big hydraulic cylinders come out the side and they lock right in. It's for safety, it's for steering, it's for maneuverability. It's one piece tied to this barge versus many barges you might see they're pulling with cables, or they're tying them all together up front and pushing. If you're on the Great Lakes, you get some weather, you get storms this time of year. It's not safe. This is an incredible technology which we leverage as much as we can. And then this is my favorite. Andrea took this picture. These are river barges. And every so often we get an opportunity to actually load into river barges over to Chicago in the Calumet River, go down into the Illinois River, and down, you can go down to St. Louis. You can go all the way down to New Orleans if you wanted to. So very effective and good way to transport recycled material. So I love the picture. The sky is beautiful, but there's more to this than just a good picture. This is a Carlin quote, and I think he's right. And I never thought about it this way. We are fueling the renaissance of the steel industry. The steel industry struggled for many years. And in the last 5 years, it's had one of the best runs ever. There was such a need with COVID. There's been some tariffs put in place so that other countries can't dump, specifically China, steel here. And our steel mills had to step up to keep up with demand. And post-COVID, the demand was just crazy. So the mills are very healthy. They're running well. But there's an interesting thing when we think about the Renaissance. In the early days, you had a blast furnace, massive, dirty, thousands of acres. You have to be on water. You take iron ore from out of the ground, then you got to refine it, and then you got to add some other things and go to an oxygen furnace. and then eventually you can make steel. They're being replaced with technology with electric arc furnaces, which I'll say is an EAF. An EAF, an electric arc furnace, is considered a mini mill. You don't need to bring hundreds of thousands of tons of iron ore in. You don't need to be on the water. You can be right where your customer or your supplier is. You can set up in a cornfield, and you need much smaller footprint, way more efficient, smaller batches, smaller lots, not millions of tons, hundreds of thousands of tons. Different types of steel and grades. Your changeover is quicker. And is there a video here? Yeah. So the EAF uses electricity, has graphite rods that go down in with high amounts of voltage. It arcs, and that energy melts the steel. Very quick process. It can melt about 150 to 200 tons every hour, and they just keep doing batches. Sorry for the quality of the video. It's very, most people in the world will never get this close to an electric arc furnace. It's dangerous. You have to be behind things, and they don't do a lot of tours. There's just a lot of safety reasons for that, but it's incredibly loud. It's arcs and sparks going everywhere. It's intense. It really is intense. But here's the best part about this renaissance. A blast furnace is 2 tons carbon dioxide per ton of steel. They use coke and limestone and iron ore, and then of course energy. And they use a little bit of scrap. A blast furnace will use 10% scrap metal, 90% natural raw materials. An electric arc furnace, an EAF, is the exact opposite. They use 90% scrap and 10% maybe a little pig iron or something else. So because of that, the emissions, the carbon footprint of a blast furnace here is 2 tons. An EAF is 0.3, 0.4, and even getting better. 5 times. More efficient, cheaper, cleaner, and 90% recycled material is used for their raw materials versus 10. So the US is 70% EAF, 30% blast furnaces. We're shuttering them, and we're building EAFs all over. The rest of the world is the opposite. They're 70% blast furnaces, 30% EAFs. So we make the cleanest, the greenest steel in the world, right here in the United States. But to feed this, and this is the renaissance, we need, let me go back. There's a couple more videos. I like pictures and videos. We need more scrap. So if you take a blast furnace, let's just say it's 200,000 tons a month, they need 10% scrap. Dave, 20,000 tons, right? Check my math. Okay. If you're doing 200,000 tons a month and you have an EAF, you need 180,000 tons of scrap to feed that. So you're going to go from 20,000 to 180,000. Where's that scrap coming from? All of you. Thank you in advance. But that's what these mills need to produce. And we want to use more of these mills. We want to feed these mills. So all that technology that you saw that Patnus is investing in is to help feed this need. It's what's best for the United States. It's what's best for our economy. It's what's best for our environment by far. And it can be done. The technology is there. Have to be committed to it, and we need all your help. Here's another shot. This is a charge hopper, the scrap. It's hard to see it through a bulletproof window, but they're dropping the scrap in a charge bucket right down into the furnace, and then the 3 electrodes go down in and just burn right through it. It's just the most incredible thing. So you can see the scrap there, and then these rods are burning right down into that. Incredible amount of energy very quickly, basically using electricity to melt scrap versus oxygen, coal, coke, and all those materials in the blast. That is technology there. That's pretty wild. Real quick, the global steel consumption, Large majority of that is construction. Mechanical engineering, other metal products. You see here globally, automotive is 9%. In the US, it's different. Construction is still about 44%. That's before the infrastructure bill. That is before the Inflation Reduction Act and all the investments that the government is pumping back into our economy. This is going to be even higher. This is going to fuel. This is that renaissance. This is that pull, that need for scrap. Automotive by us is about 28%. And right here in the Great Lakes, it's even higher. Most of the steel mills around us are making stuff for the automotive industry. So we talked about if we switch one mill with the same tonnage of product from a blast furnace to an electric arc furnace, an EAF, how much more scrap you need? That alone is just a huge gap that we need to fill. On top of that, there's 20 million tons of new EAF capacity, either just been built, being built, or going to be built in our region. And here's a list of all these mills: US Steel, Steel Dynamics, Nucor. They got 3 of them going on. ArcelorMittal, Commercial Metals, JSW, Nucor, Algoma. Now that one, I'm calling it here because it's Sault Ste. Marie. It's just across the river. Like, yeah, that's close enough. Good place to go with a barge too, by the way. They're right on the water. Very efficient, effective way. Clear down. All these in the next 8 to 10 years are coming online. If you need 90% scrap for 20 million tons of capacity, we need 18 million tons of scrap to feed this. And the scrap needs to be clean and it needs to be pure, because an EAF needs good quality scrap in order to run. So what are we going to do about this? So we need good, clean, ferrous scrap. Everybody knows that sticks to a magnet. What we don't want or can't have in that scrap is non-ferrous. What's happening to the amount of non-ferrous metals that are going into everything? Think electronics. It's going up. A conventional car has 18 to 49 pounds of copper in it. A hybrid has 85. Electric vehicle is 132, and a battery electric vehicle is 183. And you get to buses, battery buses, 800. And you see the chart and the trend. We're using more and more copper, battery, electronics in vehicles. And copper is a no-no for the EAF. They can't have that in there. It messes up the quality of the steel. So we got to get that out. That's why we are investing in all that technology we talked about for the last hour. Here's the other one that's growing even more exponentially, is the aluminum. There's more and more and more aluminum going into a vehicle. So obviously we need to be prepared and have the technology so we can get that out. And I use a vehicle or a car because it's a generic and a large volume of our scrap supply. But in anything, we're seeing more of those two metals that are valuable, that are fully recyclable. We just got to get them out so they can be recycled, so we can also make good steel scrap for these steel mills that need it. The steel mills, the EAFs, they're all looking for a low copper shred. So we have to pull those meatballs. We have to pull the copper wire, all the things we talk about, out of this shred. So it's all steel. And it's a good question back there. It has to be a high recovery steel to feed those EAFs. And then one last story, we'll wrap up and we'll take some questions. Everybody knows the power plant? Everybody want to know what happened to it? It fell down very dramatically. This is a close-up view. We actually had, ringside seats because that fence is our property right there. Isn't that incredible? Yeah, it was pretty impressive. You were right there. They know what they're doing, these demolition experts. So what happened to that? It came to Grand Rapids, to our shear. It's a processing piece of technology that I haven't talked about yet. Basically, a guillotine shear cuts up big, heavy beams into whatever length you want. We do some sorting to it, and then it can be prepared to go on and get melted. So there's a quick video here. You can see in the blue. Let this thing load. I'll click it one more time. And you can see the hydraulic cylinder going up. There's 1,000 bar It's 1,000 ton of force, and it's cutting all those pieces up. See that yellow I-beam? Was a yellow I-beam into a 2-inch piece because it goes into an induction furnace. They melt it back down. And then what do they do with that? This scrap went over to a foundry on the east side of the state of Michigan. It's melted down, was made into brake rotors, and it's currently on Dave's Tesla and Sue's Tesla. Maybe not, because unless you changed your brakes recently. But if you drive an electric vehicle or any higher end vehicle, sports vehicle, you've heard of Brembo brakes. Brembo brakes has patented scrap in it. So if you have Brembo brakes, you have a little bit of Holland, Michigan, of Holland power plant on your vehicle. How's that for a story? True story too. I call that real cycling. So with that, I'm done with the presentation part and would love to entertain as many questions as we have time for. Thank you so much for your attention.
We have a,
So to start off the questions, you talked about lots of different processes and machines and so forth. We all drive by Pine Street. How much, or and you talked about the shredder and the history of the Pine Street facility. How much of these different types of machines and process, excuse me, processes do we drive by in Holland, and or are they all spread out across the different facilities, and then moving the pieces and parts around?
Yeah,
There's got to be a big logistics if it's not all in the same place.
there's an incredible amount of logistics in recycling, for sure. So very good point. The question is, how many processing technologies and equipment do we have in Holland? More than in any of our facilities and more than any other recycler that I know. We are not the largest recycler in the country. We have a big presence here in West Michigan and of course Holland in our history. But we like to say, and I believe it's true, that we have more different types of processing technologies and we do more. We are heavily involved and invested in more different types of materials, paper, plastics, very involved in plastics, electronics, ferrous and non-ferrous metals. Many recyclers, hey, we're a plastics recycler or we're this. We like to do it all. And Holland has a briquetter, has a shear, has a shredder, has a baler, has a lab. I mean, Holland pretty much has one of each of it, other than the very technical downstream we saw, like that X-ray machine. It's such a huge investment. That's in one spot, and we have to bring that material into that. But Holland is a great representation. It's a great place to do a tour if anybody's interested. Happy to accommodate that, see some of this in real life. Dave's like, sign me up. Another question in the back.
yes, when recycling cans and bottles, is it important to rinse and remove the labels before discarding into recycling bins?
That is a good question. That is a good question. I wish Kiri was here because she'd give you the exact technical answer. The cleaner in general that scrap is, it makes it easier to recycle. However, the effort and the water and the energy you put into cleaning might offset the value because we have all this technology that's ready, set up to do that, because you might clean it, but someone else won't. So either way, I have to have the technology and I have to use it. So I think the answer is it would depend, but in general, if it's a quick, easy clean, that is always helpful and appreciated if you're working in the recycling side. So it's not so dirty when you're handling it. Question up front here. Need a mic?
We have one more question
Go ahead.
online. Since cars are lasting longer and EVs may last even longer since motors may be more reliable than engines, will the scrap flow from autos decrease because cars will have a longer life?
It's a very good question. It's something that we think about a lot. Public transit and mass transportation will actually affect us a lot more than that. The life expectancy of a car is 8 to 10 years. We see a lot of cars that look pretty nice that actually we used to, that get shredded. What's actually impacted the life of a vehicle today is the economic environment we're in. There was a chip shortage. There weren't a lot of cars available at the dealerships because the automotive industry was behind. And then now the interest rates are so high, nobody wants to sign a new lease or get another car loan to do it. So people, the last 18 months, there's been fewer cars manufactured. We used to make 17, 18 million vehicles in a year. This year we might hit 15, and it's been 13 and 12 the last couple of years. So that right now we're actually seeing that cars are lasting longer due to that. But as soon as we work through the supply chain disruptions, the inflation, the interest rates, there's a lot of people that need to buy a car. I have 3 vehicles on my lot, my property, my house, with 2 teenage drivers, my wife and myself, and all of them have over 100,000 miles. I just don't want to buy one right now. So I'm driving mine longer as well. But at some point, I'm gonna have to buy a couple, and many are in that same situation. So cars can last longer. You're right. The engines and the technology usually don't fail. Up here in Michigan, it's usually the aesthetics, the body, things like that.
I have 2 questions. With the switch from the blast furnace to the,
EAF.
yes,
Mhm.
is there any more safety for the people that work around those things? or-
Yes, yes. The EAFs are not more dangerous than a blast furnace at all. In fact, I would say, I'm not an expert, but I would think that they are safer than the ones I've been in. They're a smaller footprint. They're controlled. The melt process is just right here.
Mhm.
It's smaller batches, and it's a very controlled. Blast furnaces, very difficult to start. Once they start, they don't want to shut them down. Huge volumes. I've never been even close to a blast furnace. They won't even let you get there. So the electric arc furnaces are smaller, more module. The steel industry has a very good reputation for safety. They do a very good job. And I do not think that they are less safe. I would say the opposite. It's a good question. They're not safe to stand right next to.
Another question. Louis Padnos.
Yeah.
When did he die?
Someone can Google it. I want to say it was before my time. I want to say, I mean, he was in his 20s in 1905, 50s, late 50s. Let's look it up a minute. We'll find out. I don't know. I'm sorry. I don't know exactly
I
when.
was just wondering how much things have advanced in the
Yeah.
recycling.
And
that
Louis
he
Coetzee and
never would have witnessed.
yeah,
I mean, you know,
the things that he witnessed and the impact that he had on the recycling industry was phenomenal. The next generation was the same. And then the third generation, they just continued that. It's all of them. Looking back, it would, yeah. It's a different scope today, but in their era and in their generation, they'd made just as many technological advances. It just seems different now when we have computers and AI and X-ray technology. 1962 is when Lewis passed away. Another question? Over there.
Does the electronic processing produce as pure a product as the blast furnace? And is there any slag with that and all on those kind of issues?
Yes. It's a very good question. They can make as pure of a product. They are using 90% scrap. We can make very pure scrap, but it's not as pure as iron ore that's been refined to 100% iron. So there's other things that they have to do. So the advantages of using scrap, the emissions, the efficiencies, the cost structure, it's very, very good. They do have to pay a lot of attention, a lot of metallurgy, a lot of testing, which is why they need recyclers like us that can have our own labs and do all of our own science and leverage our own technology to give them the confidence that they can use our material. So they have to spend more attention and time on the quality of their material that they're melting to get it right, but they can still get there. Yes. The slag product out of each mill is going to be slightly different. The slag that you're going to get, I don't even know if I call it slag, but you can, on a blast furnace, is from refining the iron ore and getting all the other stuff that's the oxides and things that came out of the iron ore. The slag that you get from scrap, it can be non-metallic contamination that got encapsulated into one of these pieces of shred, pinched it in there, or it can be from some of the alloys that scrap has. A lot of scrap metal is an alloy of a couple different elements, and they need to get that out of there. Versus if you're taking iron ore, you're just getting it up and purifying it. So they both have a purifying process, very similar in concept, but it will be different because they're using different raw materials to start with. Very good question. Go ahead in the back.
Joan asks online, could you clarify how the copper and steel of motor armatures are separated?
It's a good question. So I talked about how we get the armatures and those meatballs out of the stream. Now, how do we separate them? Very difficult. So we do have a new wire chopping line that we put in. Here's some examples of the chops. You can look at it. But you have a very heavy duty shredder, and you literally have to grind it up and liberate it. And then once it's liberated, and this is separate from the car shredder. The car shredder it's like a cheese grater. There's grates in there, and they're about 6 by 8 or 5 by 7. They're a square, or sometimes they can be a 6-inch circle. Well, these meatballs are going right through. So now what you need is that same technology, but you need to do it on a smaller scale to separate that meatball about this big down. And then you take the magnets and you pull the steel out, and then you go chop the copper. So you do the same thing, but you do it offline on a separate process. Thank you. Good question. I didn't explain that the first time around.
I'm surprised how much is done outside. Just because of weather effects, especially here with snow and water, emissions. There'd just be some thoughts that I would think that you'd want to have a lot more of these enclosed or at least covered.
It's a good point. The sheer size and the space you need, it'd be a massive building. Massive building. Holland here, I think, is like 48 acres, like a 48-acre building. Then you need it tall. Like our briquetter, remember, if you can see it from the road, I mean, we're talking 3 and 4 stories up. So now I can't imagine, it'd be interesting to know how the landscape of Holland, Michigan would look like if the entire Holland facility was under roof. Because you'd have a massive 8-story, 40-acre building. So now in Europe, there are some recycling facilities and plants, not the whole yard, but a shredding operation or something like that. And they put those under buildings, but that offers and presents itself with other challenges. So now you have diesel trucks running through there. What are you doing to the exhaust? And how do you ventilate it? And, some of those things. So if we can and where we can, we do a lot of processing under roof. The bulky, big shears, shredders, you got Caterpillar cranes, trucks, traffic, things like that. Typically outdoors, kind of hard to load a barge under roof as well, right? So some of the things just rail cars can be done, typically isn't. Question over there in the corner?
I had a hard time formulating the question because it just seems like you guys are doing everything. And I'm wondering, when will garbage trucks start backing up to your facility and they go to you rather than going to a landfill?
Wow. I see that we're out of time.
Well, I know there's a lot of stuff in a garbage truck.
There could be a time that something like that could happen. And the way that I could envision that happening is if we ever went back and decided to mine old landfills and recover metals.
Okay.
The current garbage stream now, I think the general population is pretty educated. It's why we're doing this. Why I'm asking for all your help as well. We're not I don't know anybody that puts copper wire in their trash. They shouldn't, or any metallic items. So the landfills don't want it there. And typically because of its value, they don't. So the way to do it, when the need for recycling trash would be the trash from 50, 60 years ago. And there's some facilities that have done that. I don't know. It'd be interesting. We have the technology to do it, right? With everything you saw.
Yeah, I was going to say you're
Really dirty.
do
It
everything.
yeah. It would be
So-
very, very challenging from an environmental standpoint. Like what's at the bottom of landfills from the fifties and sixties, there'd be a lot of things that we'd have to take into consideration. The technology does exist. So if that business case and from an environmental standpoint, if a government would have to help and be involved, there'd be all kinds of regulatory things, but the technology is there. I would also just wonder what would be the return and the carbon footprint and the benefit of mining that all back out, transporting it all, processing it all, and how much is in there. So known sites that have had high concentrations of things, usually from a manufacturing process, and it was a byproduct, they know that that's all in one landfill, then they've gone back and done it. But just from general population, I don't know of any recycler in the United States that's done that. Technology exists.
Yes.
Is a value there. Any other question up front here, John?
I mentioned this last week, about 20 years ago, I was playing with Stuart.
That's
And
amazing.
He played way into his 80s. Two questions. One is, how many employees are there in Padnos
Okay.
about? And what happens to the tires?
Oh boy, good question. First one's easy. 1,002 yesterday. I have a dashboard. I see it every week, which has grown tremendously. Just a few years ago, we were maybe 500 or 600. And then we do internships, we do contracted labor, things like that, and summer help. So it fluctuates, but it's basically 1,000. The tires, if they're ready, shredded through the shred process. So if they are on the cars, those would end up in that fluff stream that we talked about. If we take them off, there's a company that actually will sort them all and they'll find all the usable ones and they'll repurpose them and put them back on cars and back on the street.
Back into tires?
Yeah. Like they keep the tire, they sort it, they inspect it, and then it goes into a used tire market. And then the other processing is cryogenic grinding. Freeze the tire with liquid nitrogen, get it super cold, shatter the rubber off the steel belting. You have to shatter it because it's literally hardened right around those steel belts in a tire. A radial tire has steel belts, just hundreds of this like thin cable that is encapsulated in the rubber. So you cryogenically grind it, which means freeze it, shatter the rubber in a shredding process. The rubber goes one way, the wire goes another. The wire can be recycled. That's easy. The rubber is a little more challenging, can go into asphalt roads, can go into playgrounds, things like that. Good question. Any others? Wow.
What happens to fiberglass?
Fiberglass currently is part of the waste stream. Yep, goes to the landfill. In the form that it's coming out of the shredding process and mixed with all the materials, I don't know of a way today that it can be recycled.
This will be our last question.
After the last talk we had,
Mhm.
My wife and I said, okay, we've got to look at what we can recycle, which goes in the recycle bin and which doesn't. And we started looking at a lot of the plastics and we said, well, does number 7 go in there or not? And we sort of got stymied about what exactly can be and can't be. Now, after listening to your talk, it strikes me that most everything can go in the recycling, except things like food and I don't know. Maybe everything can go in a recycle bin. Now, I'm not sure that the garbage pickup people will agree with me, but
Yeah. That is the challenge. And I think every community has a different setup. Some you separate them all, some is single stream. There's this debate that's been going on. I would suggest you follow their guidance because they're set up to recycle certain things, and typically they'll give you guidance on what they want for Holland versus Grand Rapids, the Kent County municipality, the MRF recycling facility there. And so if they're set up for something, they don't want something, then I think I would recommend you follow their guidance.
sure.
The truth of the matter is, if you work hard enough at it, we can figure out ways to recycle just about anything. I don't know that I would say everything, the cost benefit, the cost from emissions in an environmental standpoint sometimes offsets. Like, okay, I'm checking this box and I'm recycling it, but really I made the earth a worse place. And I think Carrie talked a lot about that last week. That's where the real cycling comes in, where we look at the facts and what is truly makes sense versus what feels good. And sometimes those are far apart. They really are.
Okay, that's our last question
Okay.
for the day. And first of all, I had no idea we had a high-tech company over on Pine Street. And
Wow.
clearly, it's everybody's responsibility to recycle in any way you can and to get some information from who provides recycling to you to know exactly what you can recycle. And Padnos certainly is doing their part in all the things that we can't personally impact. So thank you very much to Padnos for supporting us on these last two presentations. Thank you very much, Brandy, for coming today, and Andrea, who's also here supporting them. And he's got some samples up here if you want to get a
Sure.
close-up look of some of these items. And just want to remind you to be sure to fill out your evaluation that I just saw popped in my email. So thank you very much for coming today.
Thank you. Thank you for the opportunity.